Hello, Professor. We can
Yeah.
start.
Okay, so let's start. On Monday, we stated a description of all G-invariant variations on a spherical variety X, spherical for the action of the reductive group G, as usual. Let me recall that we denoted by E script E sub X the space of all linear functions on the weight lattice of X with values in rational numbers. And then the lemma, which we stated at the previous lecture, says, it was lemma 4. It says that G-invariant valuations of the function field of X correspond to vectors in this vector space EX, which form a solid, that is full dimensional, convex cone denoted by V script V sub X, which is called the evaluation cone. So in the quasi-affine case, we describe this cone as follows. We consider the coordinate algebra of X, and we considered two irreducible submodules in the coordinate algebra with highest weights lambda and mu, any two irreducible submodules, and their product. This is still a G submodule in K of X, and it decomposes as the direct sum of irreducible submodules with highest weights. So one of these highest weights is lambda plus mu, and the highest weights of the other summands are obtained by subtracting from lambda plus mu several positive roots. So these characters which we have to subtract, I denoted them by betas, beta 1, etc. Beta R, these betas are sums of positive roots, of several positive roots, and they are called tails. So the tails, beta i's, are sums of positive roots. Then the evaluation cone can be described by linear inequalities, can be defined by linear inequalities as follows. So the evaluation cone just consists of all vectors in this space EX, whose values on all tails are non-positive. This is for all tails, and of course for all lambdas and mu's occurring as highest weights in the coordinate algebra of X. So let me draw the picture for this. So we have like this. We have the hyperplane in the vector space spanned by characters, by the character lattice, which separates positive roots from negative roots. This is this hyperplane. So this is the origin. These are, say, positive roots. And the tails are just sums of positive roots. For instance, this vector and maybe this vector. These are tails, beta j's. And the cone given by these linear inequalities, of course, this cone sits in the dual vector space. But let me draw this cone on the same picture, thus identifying the vector space spanned by the characters with its dual. Because, well, this can be done, for instance, by choosing an inner product, but it is more correct to think about the dual vector space. Well, just just imagine that this picture denotes at the same time the vector space spanned by the characters and its dual. So this valuation cone can be exhibited here as follows, something like this. I don't know. Well, maybe like this. So this valuation cone V sub x. Actually, this valuation cone sits. This cone sits in the vector space dual to the weight lattice of X, which is a sublattice in the character lattice of the maximal torus. But we can, well, again, we can identify. When you take the dual vector space to a sublattice, it is the same as the quotient of the dual vector space to the whole lattice. But again, you may imagine, you may embed it as a subspace and consider the quotient map as a projection. So on the picture, it can be exhibited like this. So this is the picture of how things look like. And by the way, you see from this description, that the cone V sub x is indeed a solid cone. That is the cone of full dimension. Why it is of full dimension? This is because the cone spanned, so this is because the cone spanned by the convex cone spanned by positive roots is pointed. This means that it contains no line. And the cone spanned by tails, it is a subcone in the cone spanned by positive roots. So the cone spanned by tails is also pointed. While the cone V sub x is opposite to the dual cone of the cone spanned by tails. So when you have a pointed cone, then the dual cone given by linear inequalities coming from vectors in the pointed cone, this dual cone will be solid. This is an elementary.
How can we prove that it is a pointed cone?
Well, because all positive roots belong to a half space. Just look at the picture. Positive roots belong to a half space lying above this hyperplane. This means that the cone,
yes, I know.
yeah, you see this. Okay, that's good. And when the cone is pointed, as I said, the dual cone is automatically solid. So this explains the statement of the lemma that this cone is solid. But we still have to prove. We still have to prove this claim that a vector v belongs to this cone v sub x, defined by the inequalities on the previous page, if and only if v defines a G-invariant valuation of the function field. So we need to prove that this cone indeed describes G-invariant valuations. So far, we just defined this cone by linear inequalities. In fact, we have already proved at the previous lecture that these inequalities are necessary to have a G-invariant valuation. These inequalities hold for vectors coming from invariant valuations. So the implication from the right to the left was proved on the previous lecture, when we considered the products of two irreducible submodules in the coordinate algebra and the tails and so on. This we proved at the previous lecture. It remains to prove the opposite implication from the left to the right, that these inequalities are also sufficient to get a G-invariant valuation. But since we know how to recover an invariant valuation from a linear function on the weight lattice, that is from this vector in the space E sub x, there is only one way to define this valuation from this vector v. Namely, if we have a function, a regular function on x, sitting in the coordinate algebra k of x, which can be decomposed as a sum of functions sitting in irreducible summands, non-zero projections to irreducible summands of some highest weights lambda i's, well, non-zero. Then the only way to define the value, of evaluation v on this function f is to take the minimum over all i's of pairings of this vector v, which is the linear function on the weight lattice, with these highest weights lambda i's. So we deduced this formula for a G-invariant valuation on the previous lecture. And now if you want to define a G-invariant valuation from this vector v, then this is the unique way to do it, at least for regular functions. It remains to check that the map v from functions to rational numbers given by this formula is indeed a G-invariant valuation. Actually, the only non-trivial thing is to check the first condition in the definition of evaluation. Condition 1, which is the multiplicative condition. Condition 1, if you look at the definition of a G-invariant valuation, I guess on lecture in lecture 10, then this condition 1 says that the valuation map is just a homomorphism from the multiplicative group of rational functions to the additive group of complex numbers. And this multiplicative property has to be checked for the function v, which we defined in the line above. So let's take yet another regular function, say g, which can be decomposed similarly. So here g is not a group element, it is a function on x. You should be careful about that. So again, gi's are non-zero projections of this function g to irreducible summands of some highest weights mu j's, gj's, not gi's. And now we consider the product. We take the product of these two functions. And right here. Which is, of course, just the sum over all i's and j's of the products fi with gj. These products are not in irreducible. In general, these products fi times gj are not in irreducible summands of k of x. They are in products of two irreducible summands, and each of these products can be decomposed in this way using tails. So we have to look at this decomposition. We have to take highest weights which occur in this decomposition. And we have to evaluate the vector v at these highest weights and take the minimal value. This will be the value of v at f times g. Maybe again, let me draw a picture. So we have the set of highest weights lambda i's corresponding to f. Maybe I'll draw it here. These are lambda i's. Some finite set of vectors in the weight lattice. Also, we have the set of, so these are lambda i's. These are lambda i's. Also, we have a set of vectors mu j's. Again, a finite, yet another finite set of vectors in the weight lattice. This is the set of mu j's. And let us consider the vector v as the linear function of weights on weights and evaluate this vector at these weights. So we have the minimal value is achieved at some weights, and let me draw the respective hyperplane on which the minimal value is achieved. Let it be this hyperplane here. And for the other set of weights, let it be this hyperplane here. Okay. So let me indicate by an arrow the vector v considered as the linear function. So this vector v defines this hyperplane. This is the supporting hyperplane for this linear function on this finite set of vectors, on this finite set of weights. So this stands for v. And what we can do now, we can choose. Let me write it here. We can choose. Well, maybe here. Choose a weight, one of these weights lambda i's, say lambda naught, and one of these weights mu j's, say mu naught, such that the value v takes the minimal value on lambda naught among all lambda i's. So this value is the minimal one. The value of v at mu naught is also the minimal one among the values on mu j's. Okay. And another condition is that for any pair of I and j, this difference lambda I plus mu j minus lambda naught plus mu naught does not belong to the cone spanned by tails. It is possible to choose such a pair for the following reason. So let's consider all these sums, alpha lambda i's plus mu j's, all these sums. So let me again draw a picture. This is yet another picture for these sums. So here.
How can we ensure that lambda I plus mu j minus lambda naught plus mu naught?
Yeah. This is what I'm going to explain right now. So let's consider all these sums. There are plenty of weights, all these sums. So something like this. These are lambda i's plus mu j's. Again, we can consider the value of v on all these sums of weights and take the supporting hyperplane for this linear function v. So this is this supporting, excuse me, I should draw it thinner. This is the supporting hyperplane for v. So this is my v here. So here I should choose bold line. This is my v. And if I consider the cone spanned by if I consider the cone spanned by the vectors opposite to tails, then it is a pointed cone. Let me draw it here. It is a cone in the dual space, but again, it is convenient for me to draw it on the same picture. So the cone spanned by tails, let it be this one. It is a pointed cone. I put the apex, the vertex of this cone at this weight lambda I plus mu j, not at the origin, but I can do it, of course, if I want. So this is the cone spanned by tails, spanned by minus tails, the cone opposite to the one spanned by tails, okay? This one. And since this cone is pointed, you can easily choose a vector lambda naught. You can easily choose such a pair of weights, lambda naught and mu naught, such that this pair of weights doesn't belong to this cone, with the vertex put at any other of these sums. So if you move
lambda naught does not belong to lambda I, right? And just a new character.
Yeah. No. Lambda naught is one of these indices I. So naught is one of these i's. Lambda naught is in the set of lambda i's. And mu naught.
So the minimum condition is that the value of v at lambda naught is the minimum of the value of v at lambda I, right?
Right. Let me well, since such a question arises, let me write this explicitly. Okay, so let me write this explicitly here. So it is the minimal among all pairings of V with lambda i's, minimum over I.
So
And the
I
same,
have,
yeah.
if you define lambda naught and mu naught like this,
Mhm.
then the last line can be proved by applying V to the left-hand side. Because V is
well, not exactly, because it may happen. It may happen that there are several of these lambda knots, which means that so this minimum can be achieved at several weights. And then the difference of these two weights, it may in principle happen that the value of V at the difference is 0. Yeah, so this is possible. If lambda I is on the same hyperplane, on the same green hyperplane as lambda naught, and also for mu I. So this extra condition is indeed necessary.
well, if the difference, if the value of V at the difference is 0, then we cannot conclude that the difference is not in the cone of tails. Why?
Well, because the inequalities defining this V sub x are not strict. It may happen that somewhere here the difference, the value is 0. And then we cannot conclude that the difference is not in the cone of tails.
I know.
So you have to be a bit careful. It is a technical issue, but you have to be a bit careful here. But we get rid of this technical problem because this cone of tails is sharp, is pointed. And for this reason, at least we can say that we can guarantee that we can choose such a pair of lambda naught and mu naught. So, for instance, on the picture, you can take for lambda naught you can take this guy, and for mu naught you can take this guy, and lambda naught plus mu naught will be this extreme point on this line. Okay. If you take, for instance, lambda naught to be this point and mu naught be the same, then the sum will be, for instance, this guy, this point. And since we have this line, this ray in the cone spanned by tails or by minus tails, by negative tails, then it may in principle happen then that this difference will belong to the cone of tails.
So we choose the extreme point on the
yes. In a sense, we choose the extreme point. So since this cone is pointed, this condition that the difference does not belong, the condition that the difference belongs to this cone induces a partial order on weights. And we take just a minimal element in this finite set for this partial order. Okay, so you can say like this. Anyway, let me leave these technicalities for you to think over, because I think that you have to digest this construction. But look at the picture. From the picture, everything is more or less visible, and you can recover the strict argument from the picture. So yeah. So if we have chosen this pair of weights lambda naught and mu naught, then we see that actually the product of f and g decomposes as the sum of projections to irreducible submodules, say h naught plus h1 plus etc. plus maybe hr, where each, let me maybe write it here, where this H naught sits in the irreducible summand corresponding to the highest weight lambda naught plus mu naught, and it is non-zero because it comes from the product of f lambda naught and g lambda naught, from the product of f i's and g of f naught and g naught of these projections of f and g to the respective irreducible summands. And it cannot be, this projection cannot be cancelled with any other projection because of this third condition. Because all other projections coming from other highest weights are obtained by subtracting from the sums alpha I plus mu j, subtracting some tail. But you never get lambda naught plus mu naught by subtracting a tail from lambda I plus mu j. And for this reason, this h naught is not zero. And the other h case,
Excuse me.
Yes.
How is the proof that h naught is non-zero?
Because when you take, let's look here. When you take f naught corresponding to highest, f naught sits in k of x sub lambda naught, right? In this reducible submodule corresponding to lambda naught. When you take f naught and multiply it with g naught, you get a product, f naught times g naught. And this product, the product of these two non-zero functions, has a non-zero projection to the irreducible submodule corresponding to the sum of highest weights, to this guy. This we discussed on the previous lecture. That
I think the previous lecture requires us that the product of f naught and g naught is non-zero.
This is true. This is true because f naught and g naught are themselves non-zero. They are non-zero. They are non-zero projections of f and g to irreducible sums.
So this time we require the regular function on x from the integral domain.
Of course, because x is irreducible. The coordinate algebra of x is an integral domain. Yes, sure, of course.
Well, irreducible. So we not only assume that x is cosine affine, but also irreducible, right?
Well, x is assumed spherical. Spherical means irreducible.
I remember x is irreducible.
Okay. Well, let me continue then. So the other h case belong to irreducible summands corresponding to highest weights of the form lambda I plus mu j minus some tail, say beta k. And now, if we want to compute, well, do I have enough room to do it here? Maybe yes. So if you want to compute the value of f of v on the product of f and j, then by definition, you have to take the minimum or the minimum of the pairing of the pairings of v with these weights, lambda naught plus mu naught, lambda I plus mu j minus beta k, all these weights. And by the choice of lambda naught and mu naught, this minimum is reached at lambda naught plus mu naught. It is the same as this pairing. The minimum of this pairing is reached on lambda naught plus mu naught. And this is, of course, nothing but the sum v pairing with lambda naught plus v in pair with mu naught, which is by definition v of f plus v of j by the choice of lambda naught and mu naught, because they achieve minimal values. They take the values on lambda naught and mu naught are minimal among all these values. So finally, we deduce the multiplicative property. And this concludes the proof of lemma 4 in the quasi-affine case. So if you still have questions, then you can ask. Are there any questions? Well, this is indeed technical, but I mean, we have to do such technical things to get a complete proof. So this is somehow unavoidable. But if you trace the proof step by step, then it is not difficult, in fact. So some convex geometry, some commutative algebra, some representation theory. Okay. Now let's turn to the general case, non-quasi-affine case. In the general case, well, as usual, as often, I would say, as it often happens in the theory of spherical varieties, the general case can be reduced to the quasi-affine case, like this. So you have the set of G-invariant valuations.
So again, we take the affine cone on X.
Yes, the construction is always the same. It is the affinization construction, taking a affine cone or some version of it. So here we take the affine cone, but let me write first that we have the set of valuations on X, this set. And each of these valuations can be extended, as we already know. Each of these valuations can be extended to a G-hat invariant valuation of the function field of the affine cone over X, or maybe over the open orbit in X. I do not assume X be projective or quasi-projective, so it's better to take the open orbit in X. It is always quasi-projective, and take the affine cone over this open orbit. So we have this extension property. This means that the inverse map, the map from G-hat invariant valuations on the affine cone to the G-invariant valuations of X is the restriction map, is surjective. Every G-invariant valuation can be extended. This means that the restriction map is surjective. Now we know by the quasi-affine case, which we already proved, we know that this set of valuations is in a one-to-one correspondence with the convex cone, say V hat, in the vector space E sub Y naught hat. This is the vector space spanned by the weight lattice of Y naught hat. But this weight lattice contains the weight lattice of X, because we have the inclusion of rational functions. So K of X is embedded in K of Y naught hat by the pullback map. And B semi-invariant rational functions on X are embedded in B hat semi-invariant rational functions on Y naught hat. And this means that the weight lattice of X is a sublattice in the weight lattice of Y naught hat. And for the dual vector spaces, for the spaces of linear functions on these lattices, we have a surjection. So we have a surjection map from this vector space to this vector space. This map is just given by restriction to the smaller lattice. And on the level of valuations, this restriction corresponds to the restriction of valuations from this multiplicative group of semi-invariant functions to this one. When you restrict a G-hat invariant valuation, that is a valuation sitting in this cone, you get a G-invariant valuation. In other words, you have a surject, so this projection of vector spaces gives rise to a surjective map from this cone V hat to another cone V sitting in this vector space. And this cone V will correspond to G-invariant valuations on X. Since V hat was convex and solid, its image under a linear projection, under a linear surjective map, will be also convex and solid. So this finally proves the lemma in full generality. Okay. Any questions? So no questions so far. Okay. So we have discussed the weight lattice. We have discussed G-invariant valuations. And well, maybe I should also make a remark about this cone, which I forgot to say. So a remark. In fact, this cone, this valuation cone V sub x, is not just a convex solid cone. It is polyhedral. It is a polyhedral cone. It is, in fact, defined by finitely many linear inequalities. And even it is a cosimplicial cone. Cosimplicial means that maybe I made a typo. I think that cosimplicial reads like this. Cosimplicial means that it is defined by finitely many linearly independent linear inequalities. So we shall prove that the valuation cone is polyhedral. It is not that difficult, and we shall prove it later.
So what is the difference between polyhedral and cosimplicial?
Polyhedral means the cone is defined by finitely many linear inequalities. And cosimplicial means that these linear inequalities are linearly independent. They are given by linearly independent linear functions. Okay? For instance, the cone like this. This cone in a three-dimensional vector space, this cone is polyhedral but not cosimplicial. And this cone, again, in a three-dimensional vector space, this cone is cosimplicial. Okay?
Oh, and Professor, I have a question about general case.
Yes.
Sorry.
Yes.
So we have a projection map from V hat to V.
Yes.
So how is the one-to-one correspondent in the first line if the project?
Well, because let me say, because we already know that a G-invariant valuation is uniquely recovered from the respective vector in this vector space E sub x. The only thing we have to prove is that each vector in V corresponds to some G-invariant valuation. So the only thing we are left to prove here is that this map from the left to the right is surjective. But this map is surjective because this is one-to-one, and this map is surjective, and this map is also surjective. So injectivity, we already know the injectivity here.
Injectivity is from what?
Injectivity is from the previous lecture. We have proved, I guess it was lemma 1, that a G-invariant valuation is uniquely recovered from.
Determined by.
Yes. Mm-hmm. Mm-hmm. So I answered your question about polyhedral cone or about polyhedral and cosimplicial cones. Yeah, I guess you see the difference. And now let me turn to the third birational invariant of a spherical variety. It is what is called the set of colors. So we have finished with valuations, and the third birational invariant is the set of colors. So what are colors? Let me again remind you our notation. We have an open G orbit in X. Open G orbit in X denoted Y sub naught. And in this open G orbit, there sits the open B orbit, which is denoted Y upper naught. So let me write, this is the open G and B orbit in X. And since the open B orbit is affine, its complement inside Y naught is the union of finitely many prime divisors. We have already used this decomposition for the complement of the affine open B orbit in the proof of some lemma. So these D1, DS are B-stable prime divisors. They are B-stable because they are in the complement of the open B orbit. B-stable prime divisors. And now the set of colors. The set of colors which I denoted as D sub X is just the set of prime divisors in X, which are the closures of these DIs. In other words, the set of colors, the colors can be defined as prime divisors in X, which are B-stable.
Which is decomposed into B-stable prime divisors, the complement of Y.
The complement of Y upper naught in Y lower naught. The complement of the open B orbit in the open G orbit.
This complement can be right.
I'm sorry. I'm sorry. I see that I have written something stupid here. So let me. What I said orally was true, but I have written a wrong formula. So the complement of Y upper naught in Y lower naught is decomposed as the union of finitely many B-stable prime divisors. Now I hope the formula is okay. It is clear now. Okay. Okay, so the set of colors can be also defined as the set of all prime divisors in X, which are B-stable, but not G-stable. G-stable means that a G-stable divisor lies in the complement of Y lower naught, in the complement of this open G orbit. But we consider only divisors which intersect the open G orbit, which are the closures of the divisors in the complement of the open B orbit in the open G orbit. So this is the same as written here. So all divisors in X, which are B-stable but not G-stable. This is a finite set.
Why the closure of DI is not G-stable?
Well, because DI itself is not G-stable. DI itself is open and dense in its closure.
Yes. I see. DI is not, does not lie in the.
Maybe again, let me draw a picture for you, as I always do. So we have this X. We have an open G orbit in X. Y lower naught. And we have the open B orbit in here. Y upper naught. So what is a color? A color is a divisor like this. It is in the complement of the open B orbit, but it should intersect the open G orbit. And for instance, this divisor is not a color. So this is not a color. And this is a color.
The black is G stable, right? So it is not a color.
Yeah. This black divisor is G stable because it is in the complement of the open G orbit. So that's why it's not a color. And this red divisor is a color. And also we have a map. Well, I see that I have to finish the first half of my lecture, but I still have a couple of seconds to say final words about colors. So we have a map from the set of colors to the dual of the weight lattice, which of course sits in this vector space E sub x, taking a color D to the vector in the dual of the weight lattice, that is a linear function on the weight lattice with integral values, which is obtained as follows. You take the valuation corresponding to D, and you take the respective linear function on the weight lattice given by restricting this valuation to B semi-invariant functions. So this notation was already used for G invariant valuations, but now we use it for valuations corresponding to colors. But this map needs not to be injective. It may be not injective in general.
Well, dx is the linear combinations of the closure of di, right?
No, it is not. It is just the set. It is not the set of linear combinations. Just the set of prime divisors.
So, what is the overlying on the?
Let me recall this notation. So let me recall. By the way, let me say that I finish the first half of my lecture right now, and now I answer questions. So the first question was about what is this VD bar, yeah? And let me recall that we have the following picture. We have an exact sequence. Sorry. Yeah. Do it in black. We have an exact sequence. 1 goes to k cross, goes to k of x over b in brackets, goes to the weight lattice, goes to 0. And if we have a divisor, we have a valuation corresponding to this divisor. We can restrict this valuation to semi-invariant functions. You get a group homomorphism from this group actually to z, in this case even to z, because the vanishing order of a function is always integer. And constant functions map to 0. And that's why this valuation gives rise to a linear function on the weight lattice, which is denoted by this bar.
So in this section, you make a difference about the valuation and the linear function.
Exactly. Here it is important because this map from D to VD bar or from VD to VD bar may be not injective.
So you do not use the notion about section 2 because in section 2 they are one-to-one correspondence.
Exactly. In section 2 there was a one-to-one correspondence between G invariant valuations and some vectors in this space. But here the correspondence is not one-to-one. different colors may map to one and the same vector. Okay. Okay, so more questions, if there are any. Okay, let me then switch off my microphone for a while, but if you still have questions, just ask it. Oh, maybe I should read the chat. Maybe there is something in the chat. Well, it seems that there are no questions. At least the one set of. So a question from Mike. What is the question? Set of colors, set of CI. So Mike, if you still have this question, could you ask it orally? Or maybe you already got an answer. And this question can be discarded. And also there is something in Chinese which I cannot translate, I'm sorry. So if this is a question to me, then please, again, ask it loudly. Well, no questions so far, then let me turn off my microphone for a while, but I'm still here. Okay, let's continue. So we introduced the set of colors, and it is clear that this set, together with this map, this set of colors, together with this map from this set to the dual of the weight lattice, essentially does not depend on X. it depends only on the open G orbit in X, or in other words, on the birational class of X, on the G birational class of X. Just because all colors intersect the open orbit, and there is a one-to-one correspondence between colors and these divisors in the open orbit, the complement to the open, the components of the complements to the open B orbit. And when you pass to an open subset, then the valuation corresponding to a divisor does not change. The rational functions will be the same on the open subset, and the valuation will be the same. So if you consider the set of colors as an abstract finite set equipped with this map, then this set and this map will not change up to a bijection, up to a natural identification, when you replace X with an open subset or add something on the boundary. So take another spherical variety birationally isomorphic to X. So indeed, the set of colors is a birational invariant of X, as the weight lattice was and the set of G invariant valuations was. So to summarize, to each spherical variety, so let's summarize. To each spherical variety X, we associated the following data. First, the weight lattice, which is a sublattice in the character lattice of the maximal torus. Secondly, the evaluation cone, which is a solid convex cone in the vector space spanned by the dual of the weight lattice. So this is the vector space consisting of linear functions on the weight lattice with values in Q. And the last ingredient is the set of colors, a finite set, equipped with this map to the dual of the weight lattice. Which is a sublattice generating this vector space E sub X. So we have this triple of data, lambda X, Vx, and Dx, equipped with this map. Let us call this the color data of X. This color data depends only on the birational class of X, as we already explained. And in fact, the color data provide a playground to work with spherical varieties in practice. It is in terms of color data that will give a classification of spherical varieties and study the geometry of spherical varieties. Let me draw again a picture how the colored data look like. So we have this vector space. We have this vector space E sub X. Something like this. This E sub X is a finite dimensional vector space spanned by the lattice dual to the weight lattice. So let me indicate by points. Well, actually, there are plenty of these points, but.
Well, Professor, the third data is the map from dx to the weight lattice, or just the image of the
No. We have to remember this map, because as I already explained, this map is not one-to-one. It is not injective. So we have to remember both the set dx as a finite set and the map from this finite set to the dual of the weight lattice. We have to remember the map. So let me draw the, sorry for taking, it takes time, but I want to make this picture clear. So let me draw the points corresponding to the weight lattice, or better to say to the dual of the weight lattice, because these are points in the vector space E sub x, spanned by this dual lattice. So here are these points. We have a vector space equipped with a lattice, generating this vector space. So the origin is somewhere here, one of these points. Say, let this be the origin. And we have a cone sitting in this vector space. Let it be, say, this cone. This is our valuation cone. This is the valuation cone. Something like this. And also we have a finite set of vectors in the dual lattice corresponding to colors. Well, for instance, this vector, vectors or points, whatever you may say both ways. This is a color, maybe this is a color. Well, let this be the color. And also, some of the colors may get to the valuation cone. It is always also possible. It may happen like this. And some of the colors can map to one and the same point in the dual lattice. So, for instance, these points, maybe better to take this. So this point corresponds to two colors. One of them is green and the other one is yellow. Okay?
Hey, Professor, what is the definition of remembering dx? Well, we just consider dx as a finite set.
Exactly.
Or we consider the birational type of the elements in dx.
Well, as I explained, if you have two spherical varieties which are birationally isomorphic, then there is a natural bijection between the sets of colors for these two varieties. So we may take one and the same abstract finite set for the whole birational class. And the elements of this finite set correspond to colors, to true colors on each spherical variety in this birational class. So if
I'm not asking this question. I'm asking for so here X is a spherical G variety, right? With a G action.
Yes, sure.
So if we want to determine the birational class of X, we must know its colored data, right?
Let me say like this. We do not raise, for the moment, we do not raise a question of determining the birational class of X. we are not recovering.
I'm not mean that. I mean, well, there are many why not type for a spherical G variety X, right? Well, different homogeneous space can all be spherical homogeneous
Yes,
space, right?
yes. Mm-hmm.
So for these different Y, we have different dx, right? Because dx is only
I mean, let me say, I mean, if you consider dx as a geometric set, as a set of divisors somewhere, then of course they will be different. But if you consider dx as an abstract set, so if you consider this colored data just combinatorially, you have a lattice, you have a cone, you have a finite set equipped with a map to the dual lattice. So this is a combinatorial object.
So we only consider the combinatorial structure, right? Not about the geometry.
So the answer is that the classification of spherical varieties in a given birational class can be formulated in terms of colored data considered as a combinatorial structure.
So this means that the number of the size of the set dx with other combinatorial information can uniquely determine the birational type of the divisor in dx, right?
The birational type of the divisor. Well, I'm not sure I understand your question well.
I mean, we can determine the birational type of the divisor just by the number of the divisor and the other combinatorial element information.
No, I mean, if you have two divisors, two colors mapped to one and the same vector, then you cannot distinguish them by this.
No, I'm not mean that. I mean the number of dx, the size of dx determines the set of divisors geometrically, not only their numbers but also their algebraic.
Let me say like this. If you fix a birational type, this means that you fix this orbit y naught. Okay, you fix this orbit. If you fix this orbit,
fix the orbit, then dx is uniquely determined.
Of course,
I'm not asking question about this. I mean, well, different y naught can be detected only use the size of dx. Right?
No. That's not true. For different y naught, dx may be of the same size.
I mean, if I'm not mean same size. I mean, well, I think I have to send an email.
Okay. Let's discuss it by email. But let me say that we maybe it partially answers your question. We do not compare color data. So far, we do not compare color data corresponding to different spherical homogeneous spaces. We fix one and the same spherical homogeneous space, and we study color data for this homogeneous space and all spherical varieties which are embeddings of this given homogeneous space. So the homogeneous space y naught is fixed. We do not compare this y naught with the other spherical homogeneous spaces. So this means that we fix this combinatorial structure and do not compare it with other combinatorial structures of the same kind. But anyway, if you still have a question, just write me on email. Now, maybe let me consider an example. I want to show you an example how the color data may look like in a concrete example, in a particular specific example. So my example will be, so let me turn to the next page maybe. My example will be the group G itself. So my X will be the group G itself, but acted on not by G, but by double G, G cross G, where the first factor acts by left multiplication and the second factor acts by right multiplication. We already considered this. It is one of the examples of symmetric spaces. So the stabilizer for this action is the diagonal G. And the diagonal G is a symmetric subgroup in G cross G. So it is a symmetric space, and then therefore spherical. In this G cross G, we can choose a Borel subgroup, which is B minus cross B. B is a Borel subgroup in G, and B minus is the opposite Borel subgroup. So B minus cross B is a Borel subgroup in G cross G. I want to describe, and also let me remind you that the open B orbit, Y upper knot, in this case, is what is called the big cell. It is the product B minus times B, or in other words, U minus times T times U, where T is the maximal torus in B, U is the unipotent part of B, and U minus is the unipotent part of B minus. This is the open cell, the big cell, which is the open Borel orbit in this variety. And what I want to do, I want to describe the colored data in this case. So let me start with the weight lattice. So if I take any semi-invariant function with respect to the Borel subgroup, so the rational function on G, maybe let me put it one line below. Okay. So a rational function on G, which is a semi-invariant with respect to the chosen Borel subgroup. Then, if I restrict this function to the open cell, to the big cell, and evaluate the function on this open cell, so let's compute f of u minus times t times u. So these small letters denote elements in the respective subgroups, big U minus, big T, and big U. So since F is B semi-invariant, B minus cross B semi-invariant, I can discard U minus and U because the characters vanish on unipotent elements. They are identically 1. And we have that this is just F of T. And again, by semi-invariance, f of t is t to some character. Lambda is a character of t times f of e at the identity, where lambda is...
F is semi-invariant, so why is the first equality correct? I think there is some constant.
The first equality is correct because every character of B minus cross B vanishes on U minus and U.
Oh,
vanishes means is identically 1.
Oh, we should use the unipotent subgroup.
Exactly. These are unipotent elements, and all characters take value 1.
T belongs to the maximal torus. Oh, I see.
And T belongs to the maximal torus, and when you shift the argument by T, it is the value of the function is multiplied by this character. So this is how the value of a semi-invariant function can be computed. And what is the eigenweight? Let's make a more detailed computation. If you act on this function f by an element in the maximal torus of B cross B, it is just T cross T. So T1 and T2 are elements in T, and this pair is in T cross T. If you act by this element on a function f and evaluate this at T, it is the same as f of T1 inverse times T times T2. And by the above formula for the function f, it is the same as T1 to the power minus lambda times f of t times T2 to the power lambda. So this means that the eigenweight of this function is a pair minus lambda comma lambda. So the weight with respect to the first factor, with respect to b minus or to t sitting in b minus, the weight with respect to the first factor is minus lambda, and the weight with respect to the second factor is lambda. So this is the eigenweight of any semi-invariant function, and this means that the weight lattice is just, so in my notation it is lambda sub g. It is just the set of all such pairs minus lambda comma lambda, where lambda ranges over characters of t. In other words, it is a sublattice in the character lattice of t cross t, which is just lambda of t taken twice. Lambda of t plus lambda of t. A sublattice which is the anti-diagonal of this direct sum. And it is isomorphic as a lattice, it is isomorphic just to a single copy of lambda of t, of the character lattice of t.
Oh,
okay?
Well, why isn't it a minus lambda? I mean, ft equals t minus lambda.
Because here we have minus, lambda.
Oh, I mean,
Here we have lambda.
Since f is semi-invariant, t acting on f should be f minus the inverse of t times something. I mean, the action on f should be the inverse action on the variable.
This is what is written here. So the action of t1 is by left multiplication, and we act by left multiplication with t1 inverse. But the action of t2 is by right multiplication. When you act by right multiplication, you already have to take inverse. And here you have take inverse to inverse. So you multiply by t2 itself. So this formula is correct.
I mean the above line, the second equality. Ft
this line.
Yeah, this line, yes.
Okay, so this lambda comes, for instance, you may consider here t acting on the right on the point E. So you take f at the point E, at the identity point, and act by t on the right. This means you multiply by t inverse. But when you act by a function, you multiply by t inverse, and you get t here.
So the lambda is corresponding to acting on the right.
Exactly. This lambda is corresponding to the action on the right as is visible from this line. Okay? And then minus lambda will be corresponding to the action on the left. So this is the weight lattice. Now let's describe the valuation column. To describe the valuation column, we have to consider irreducible submodules in the coordinate algebra of G and analyze their products, as we did before. So, what are irreducible representations of G cross G? Irreducible representations of G cross G. The irreducible representations of the direct product of two groups are just tensor products of irreducible representations of the factors. So the irreducible representations of G cross G are of the form V of mu tensor V of lambda, where mu and lambda are some highest weights, And each pair of highest weights mu and lambda gives rise to an irreducible representation of G cross G. So when does such an irreducible representation of G cross G embed in the coordinate algebra of G, acted on by G cross G as above? So by Frobenius reciprocity, it is if and only if when you take the dual representation, so V of mu star tensor V of lambda star. If you take the dual representation, and if you take, let me move it slightly to the left, like this. So if you take the dual representation and you take the invariant vectors in this dual representation with respect to the stabilizer, that is with respect to the diagonal G, embedded in G cross G. Then this subspace of invariant vectors should be non-zero. So if this subspace is non-zero, then this irreducible G cross G module embeds into K of G. This is by Frobenius reciprocity.
Why is the tensor product irreducible?
Well, it is general representation theory. I mean, the general statement is that if you take two irreducible representations of two groups and you take their tensor product, you get an irreducible representation of the product group, and vice versa. Any irreducible representation of the product group comes this way, in this way. This is a general statement from the representation theory. I'm not going to prove it. Sorry. This equivalence is by Frobenius reciprocity, which we discussed some time ago. Now let me also remark that this tensor product V of mu star tensor V of lambda star is just the same as the space of linear maps. The space of linear maps from the space of linear maps from V of mu to V of lambda star. And when you take invariants under the diagonal action of G, it is the same as to say that you take G equivariant linear maps from V of mu to V of lambda star. In other words, you take homomorphisms of G modules. You take homomorphisms of G modules. So this is the same vector space, or maybe isomorphic, better to say isomorphic to this vector space. Now we want this space to be non-zero. Yes?
The G in the upper right corner means what?
So the whole notation, hom G, means homomorphisms of G modules.
But
maybe
G modules is written in the right lower corner, I think.
You think it's better to write it here, yeah? Okay, no problem. Let us write it here. Now it's more clear. Is it better now?
Oh, okay.
Okay. So now by Schur's lemma, when the space of homomorphisms between two irreducible G modules is non-zero, if and only if these modules are isomorphic. So this holds if and only if mu, if and only if mu equals lambda star. Okay? So we know which irreducible representations of G cross G occur in the coordinate algebra of G. as irreducible summands in the coordinate algebra of G. And actually, we can write down explicitly how V lambda star tensor V lambda embeds into K of G. Let me do it on the next page. So this embedding of V of lambda star tensor V of lambda into G cross G maps this tensor product onto what is called the space of matrix entries. The space of matrix entries of the representation V of lambda. Let me denote it like this. It is a subspace of functions on G defined as follows. So it is the linear span of all functions of the following kind. You take a couple of vectors in V of lambda and in its dual, and you define a function like this. F sub V star comma V of G is defined to be the pairing of V star with GV. For any V in V and V in V of lambda and V star in V of lambda star. So you take all these functions on the group G, all functions on this of this kind.
So where is the matrix come from? The matrix is.
I'll just explain it in a moment. Yeah. So you take all functions of this kind and take the linear span of them.
Hey, Professor, I want to see the last page. I have some. I think.
Just a moment. Let me finish what I'm writing now, and then we'll turn to the last page. Excuse me. So this is called the space of matrix entries. Space of matrix entries. Space of matrix entries for the representation of G in V of lambda. So why matrix entries? Just because if you take for V and V star the elements in the basis of V of lambda and V of lambda star, the bases which are dual to each other, then this function F sub V star V of G is just a matrix entry of the linear operator, of the representation operator corresponding to the element G, the matrix entry of this linear operator corresponding to the chosen pair of basis vectors in V and V star. This explains the namespace of matrix entries. Now you wanted to see the previous page, okay?
Yes. I think the Frobenius reciprocity does not apply like this. I think the reciprocity is about the equivalent of two Hom set. I mean.
Exactly. It is about induction and restriction. But this space K of J, space K of J is just the representation induced from the trivial representation. It is the representation of G cross G induced from the trivial representation of the diagonal G. The functions on a homogeneous space is just the representation induced from the trivial representation of the stabilizer.
What? I don't follow, I think.
Let me repeat that the space of functions on a homogeneous space is the same as the space induced, the representation space induced from the trivial representation of the stabilizer. this guy is induced from the trivial representation. And when you apply the Frobenius reciprocity, then, actually, I don't want to go into much details here, into many details here, because we already discussed.
Go on. I will do it myself. Wow.
Yeah, because let me just give you a clue. We already discussed this kind of things when we considered spherical homogeneous spaces and when we considered the multiplicity-free property for spherical homogeneous spaces. Just look at this lecture and you will see that it is the same thing. Okay? So let me come back to the last page. We have the space of matrix entries, and it is a G cross G submodule in K of J, which is isomorphic to this tensor product. The isomorphism is just given by sending V star tensor V to this function f sub V star V sitting in this space. Okay. This is this isomorphism given by this map. If we take the highest weight vector in this tensor product, the highest weight vector in here, corresponding to the chosen Borel subgroup B minus cross B, then this highest weight vector will be the product, the tensor product of V minus lambda star tensor V lambda, where V minus lambda star is the lowest weight vector in this V of lambda star. So the lowest weight vector for B is the same as the highest weight vector for B minus. So this guy is the highest weight vector for B minus cross B. And this highest weight vector maps to a B minus cross B semi-invariant function of eigenweight minus lambda, comma lambda. So in our previous notation, this space of matrix entries is what we denoted previously as K of J sub minus lambda, comma lambda. This is the irreducible summand in K of J with this highest weight, minus lambda, comma lambda. Okay? So we describe the decomposition of the coordinate algebra of G into irreducible G cross G submodules. And now, if we consider the product of these two submodules, it corresponds to the tensor product of representations. So let's take the tensor product of two representations of G, V of lambda, tensor V of mu. It decomposes as V of lambda plus mu plus V of lambda plus mu minus beta 1 plus so on plus V of lambda plus mu minus beta s, where these beta j's are sums of positive roots, as we already know. And what is the product of the respective spaces of matrix entries? Matrix entries of V of lambda times matrix entries of V of mu. This product space is the same as the space of matrix entries in the tensor product of two representations, V of lambda tensor V of mu. Well, because when you tensor the vector spaces, then when you take tensor product of linear operators in vector spaces, then the matrix entries of this tensor product operator are just products of matrix entries of two given operators. Okay, so the space of matrix entries of this tensor product can be described as the sum of the spaces of matrix entries of the summons. Because if you decompose this representation space as the direct sum, then in the properly chosen basis, the matrices of representation operators in this decomposition will be of this form. They will be, how to say, blockwise diagonal, yeah, like this. So we have these blocks. Maybe put it here. Yeah, something like this. So that you have zeros here, and something on the diagonal. These diagonal blocks are just matrices for the representations in the summons of the decomposition in the decomposition of the tensor product. Okay. And therefore, this space of matrix entries is just the sum of the spaces like this. Plus, etc. Well, maybe it's better to write it differently, because there may occur repetitions in this set of beta j's, and when you take functions on the group, when you take matrix entries, it suffices to take only distinct beta j's. So the sum over pairwise distinct beta j's of these spaces of matrix entries in the representation.
The distinctiveness comes from the multiplicity free.
Oh, well, here it comes just by this calculation. Let me explain. Of course, it is related to the multiplicity free property, but here it comes just by the very simple reason, because if you have two isomorphic summons here, say beta 1 and beta 2 are the same, then we have two identical blocks here, and here, and the matrix entries here and here will be the same. So you may take just one of these blocks and forget about the other one. The space of functions will be the same. Okay? And of course, it is
if we
related.
only consider the space of functions, then they are the same. Oh,
yes, we concern the space of functions on the group, the space of matrix entries. Yes. So now let me also remind you about another notion in the structure theory of algebraic groups, or Lie groups, or Lie algebras. So we have the root decomposition. We have roots, yeah, corresponding to the choice of the maximal torus, and positive roots correspond to the choice of the Borel subgroup in G. And there is also a notion of simple roots. Simple roots. Let me denote them by alpha 1, etc., alpha sub L. these are positive roots which form a base of the root system. In other words, they are linearly independent. And any positive roots can be decomposed as a sum of these alpha i's. So among all positive roots, we can choose finitely many linearly independent roots such that any other positive root is a sum of several simple roots. So maybe let me give you a reference. There are, of course, many reference books discussing the structure theory of reductive and semi-simple algebraic groups or Lie algebras. For instance, you may take the book by Onishik and Winberg, which I mentioned when I gave you the reference list. Maybe Onishik and Winberg from the reference list, which is, the title is Lie groups and algebraic groups. Lie groups and algebraic groups. Chapter 4 and paragraphs 1 and 2 there. So in these paragraphs, the root decomposition, positive roots, simple roots, and all these things are discussed in detail. So just consult this textbook for details. Now, recall that we are studying the product of two spaces of matrix entries, matrix entries of V of lambda and matrix entries of V of mu. We want to understand how it decomposes in irreducible summations. And if lambda and mu are what are called strictly dominant weights, so if lambda and mu belong to the relative to the interior of the positive Weil chamber, so some time ago I denoted the positive Weil chamber by C plus, and the relative interior, let me denote it by this upper knot superscript. So if lambda and mu belong to the interior of the positive Weil chamber, then actually all simple roots occur in the list of tails, in the list of these beta j's. All simple roots occur in this list of tails for the product of two spaces of matrix entries. All simple roots occur among beta j's. This is an easy exercise again in representation theory. If you know representation theory of reductive groups, let me just describe it in a very sketchy manner. So if lambda and mu are in the interior of the positive Weil chamber, then you may take the highest weight vector, V sub lambda, and apply the root vector in the Lie algebra corresponding to the root minus alpha I, to the negative simple root. And also apply the same root vector to the highest weight vector in the second irreducible G module, V of mu. And if lambda and mu are in the interior of the Weil chamber, then both these vectors are non-zero. And you may take an appropriate linear combination with some coefficients, so C of lambda times E minus alpha I applied to V lambda tensor V mu, plus or minus, maybe better to write minus C of mu times V lambda tensor E minus alpha I applied to V of mu. And this will sit in V of lambda tensor V of mu. And you may choose the coefficients C lambda and C mu in such a way that this will be a highest weight vector. Highest weight vector of highest weight of weight lambda plus mu minus alpha I. Well, for some C lambda and C mu. This is why alpha I occurs among tails, and this holds for any I. Now we conclude
E minus alpha I.
This is the root vector. So recall that we have a root decomposition. So this E minus alpha I is a root vector spanning the root subspace corresponding to the root minus alpha I. This is a generator of the root subspace in the Lie algebra corresponding to this root. Okay? Just recall the root decomposition.
So E minus alpha I is an element.
Is an element in the Lie algebra. So this sits in the Lie algebra of G. The Lie algebra of G acts on the representation space.
So the product is the product of matrix, right?
Yes. The product of a matrix and a vector. So the matrix E minus alpha I acts on the vector V lambda, for instance. This is the representation of the Lie algebra of G in the vector space V of lambda or V of mu. Okay?
So since lambda mu belongs to the interior, the multiplication is not zero, or other.
Yeah, I mean that this statement comes from this. Well, I will not explain this in detail why it is so. You just have to look at the structure of irreducible representations of reductive groups or reductive Lie algebras. For instance, looking in this, you can find details about that in this book of Anishik and Winberg, for instance. So this non-vanishing comes from that lambda and mu are taken in the interior of the wild chamber.
So what is C lambda and C mu?
Some coefficients. So well, maybe.
You mean that there are some C lambda and C mu such that the
yes
the difference of the two vector belongs to the the highest weight.
Yes, you can choose them in a proper way so that this linear combination will be a highest weight vector. Exactly. Well, I think that my time is over, so let me finish. We have just computed all necessary things to describe the valuation call. Let me describe the valuation call now. So the valuation cone V sub G in this case will be given by inequality, as always, it is given by inequalities defined from tails. So it consists of vectors in the vector space spanned by the dual of the weight lattice. The weight lattice was already identified with dual of the character with the character lattice. So all vectors sitting in this dual lattice tensor Q, tensor over Z, of course, such that the pairing of V with any tail is non-positive. But tails are positive linear combinations of positive roots, and all positive roots are positive linear combinations of simple roots. So it suffices to evaluate V at simple roots. And the inequalities, the defining inequalities will be like this. So we see for any, let me add that this should hold for any I ranging from 1 to L. These are the defining inequalities of the evaluation cone, and we see that the evaluation cone in this case is just the negative Weil chamber. The negative Weil chamber in the dual space. Because the positive Weil chamber, which we denoted C+, sits in the space spanned by characters, by the lattice lambda of T. And this cone sits in the space spanned by the dual lattice, by the lattice of co-characters. So we have Weil chambers both in the lattice of characters or in the respective vector space, in the linear span of the lattice of characters, and both in the linear span of the lattice of co-characters in the dual lattice. So the evaluation cone will be the negative Weil chamber in this dual space. Okay, so I have to stop now. If you still have questions, then I'm ready to ask.
I have questions about the last page.
The previous page.
Yes, the previous page.
Okay.
Previous. So it is called the space of metric entries. If Vi and Vi star are the basis of the two irreducible representation, do we require the bases are dual to each other or any basis?
Oh, well, it doesn't matter. If you take the bases dual to each other, then you get exactly the matrix entries in the usual sense. The entries of the matrix of the linear operator corresponding to G under the representation. But if you take any other basis vectors or even not basis vectors, they are just linear combinations of the vectors of dual basis, right? You can express any vector as a linear combination of the given basis. And if V and V star are linear combinations of the vectors in the dual basis, dual to each other, then the respective function will be the linear combination of the respective matrix entries. And since we take the linear span here, we get all these functions. Okay? So in the definition of the space of matrix entries, it suffices to take V and V star ranging over the dual basis of V lambda and V lambda star.
I know this. I'm just asking the no, I do not have problem now. And about the color data, or I still want to discuss about the color data.
Okay.
Yes. So the third information about the color data is that we is the third information described as we have a finite set and we know how the finite set is mapped into the lattice. Just this, right?
Yes.
So we just know that dx is a finite set and nothing more.
Well, if you consider this combinatorially, if you consider this color data combinatorially, if you forget their origin, if you forget that the color data came from some geometric object, then yes, in the combinatorial language, it is just.
So color data is not about the source, right? Just about combinatorial information.
Yes, you may say like this. So what we need for classification of spherical varieties with a given homogeneous space as an open orbit, what we need for this, it is just this combinatorial object.
So just a map from a finite set to the lattice, right? Nothing more.
Yes.
Not about what exactly the finite set does not matter. Just a finite set and the map.
Yes, yes, you may say like this. Well, when you
I know.
when we'll formulate precise theorems about the classification, maybe you will see what is meant precisely. That this colored data is considered only as a combinatorial structure. So we'll formulate precise theorems about classification and some geometric properties in terms of this combinatorial structure. You will see. Okay. More questions or comments? Whatever. Well,
I
we
have
didn't
a
finish.
question.
Yes, please. Go ahead.
When you choose some element in the anti-dual cone of the tail vectors, then you want to define a valuation, right?
Could you please repeat this? Could you please say it again, because the connection was on my side was not so good.
So in
Please
the
repeat.
first part of this lecture,
Yes.
we prove that an element in the anti-dual cone of the tail vectors is a valuation, right?
We proved that each vector in this cone corresponds to a valuation, to a G-invariant valuation of the function field of X.
Yes. So when you check this valuation on a multiplication of two functions, I mean, if you have some f lambda naught and g lambda naught.
You mean this discussion?
Yes, yes. So why you always have a non-zero component on the part kx
on this part, yeah, on
right,
this part. Well, we discussed this actually on the previous lecture. Let me maybe open the notes of the previous lecture and show you where we discussed this thing. It was no, it was not here. It was here. So if you take the notation here is different. It is lambda and mu, and now it is lambda naught and mu naught. But you easily understand what is meant here. So when you multiply some function, some non-zero function from this space, with a non-zero function from this space, I claim that this projection will be non-zero because of the following. Because for some of these functions, this projection will indeed be non-zero. For instance, you may take highest weight vectors in here and in here. And when you multiply them, you get just the highest weight vector in here. Well, I guess it is written here. So when you multiply f lambda with f mu, you get f lambda plus mu. Again, the highest weight vector of this highest weight, and it will be non-zero because you multiply two non-zero functions. Okay?
So the f lambda and f mu here are the highest weight vectors.
Exactly. So for highest weight vectors, this is true.
Okay.
But this means that the product of these two subspaces, has a non-zero projection on this space. Yeah.
But now you choose an arbitrary function from.
Yes. Now you choose arbitrary functions. But the claim is that the projection of this tensor product, if you take the projection of this product onto this summand corresponds to the projection of this tensor product to this summand, right?
Right.
And now, when you take two non-zero vectors in here and here, take their tensor product and project onto this summand, this corresponds to multiplication of sections of the respective line bundles over the generalized flag variety. Because this representation space is nothing but the space of global sections of this line bundle over G mod B, okay?
Yes.
And also this. And when you multiply, when you take a tensor product of two non-zero vectors here and project onto here, this is the same as taking two non-zero sections in here and in here, and take their tensor product, which will be the section of this line bundle. of the tensor product of these two line bundles.
Okay.
But when you take a tensor product of two non-zero sections, you get again a non-zero section, clearly.
Well, I'm a bit confused because in this tensor product, you only have one component. So your project is
exactly.
to,
So let me say that when you just take a tensor product of two representation spaces, you get many components.
yes.
And one of these components is this space, right?
Right.
Now, when you take a tensor product of, so what does it mean geometrically? Geometrically, when you take the tensor product of these two spaces of global sections, you get the space of sections over the product of two varieties. So you get the space of sections of a line bundle on G mod B cross G mod B on the double flag variety.
Okay.
This is what is called the exterior or outer tensor product of line bundles. It is not the line bundle on the same variety. It is the line bundle on the double variety. But when you restrict onto the diagonal, you get this line bundle on G mod B again.
Okay.
And this restriction to diagonal corresponds to projection of this tensor product to this summand. By the way, this occurred already on the first lecture when we considered the Clebsch-Gordon formula. We gave a geometric proof by considering line bundles over P1, if you remember. So this is exactly the same construction. Okay?
Okay.
I have a question, Professor, about the highest vector of V lambda star tensors V lambda in G times G.
This is, excuse me, this is about this lecture or previous lecture?
Today's lecture.
Okay, then let me come back to this lecture.
I think is the second last page, I think.
This one?
Yes. What is V star minus lambda mean? I mean, I don't think this vector belongs to V lambda star.
Let me explain. So V lambda star is the dual G module to V of lambda. Okay?
Yes.
If you consider the eigenweights of the maximal torus in the dual module, then the eigenweights in the dual module will be the opposites of the eigenweights in V of lambda. Okay?
Well, does that mean that the lambda star equals minus lambda?
So I didn't finish yet. Let me finish. So the eigenweights in here are opposite to the eigenweights in here. Here we have the highest weight, lambda. This means that here we should have the opposite weight, minus lambda. This highest weight, lambda, was the biggest one among the weights here. And this weight minus lambda will be the smallest one among the weights here. All other weights in here.
So the highest weight in V lambda star is lambda star, and the lowest weight in V lambda star is lambda.
Exactly. Let me again write explicitly that this guy is the lowest weight vector for B in V of lambda star. And the lowest weight vector for B is the same as the highest weight vector for B minus. Okay?
So there is no algebraic information about the highest weight in V lambda star, just an involution.
Well, I mean, this involution can be written explicitly. If you know the representation theory of reductive groups, you can say that this involution star is given by taking the action of the longest element in the while group and taking minus. So you apply the longest element in the while group to lambda and then take the opposite weight. This is exactly the star map. Exactly.
So lambda star differs from lambda minus by the longest element in the while group.
Exactly, absolutely. Lambda star is obtained from minus lambda by applying the longest element in the while group. Again, you can consult this book for all things of this kind. It is written there in detail. Okay. More questions or comments? Well, we didn't finish the example. We described the weight lattice in this group type symmetric space G, which is G cross G modulo the diagonal G. We described the weight lattice. We described the evaluation cone, but we didn't have time to describe colors today. We'll do it on Monday, at the beginning of the next lecture on Monday. We'll describe colors for this vector space, and this will give us the color data in this concrete example, in this particular example. Okay, so if there are no more questions left, or comments, or whatever, then maybe I'll stop sharing the whiteboard and say goodbye to all of you. See you on Monday, on the next lecture on Monday. Bye-bye.
Okay, thank you for the lecture. Bye-bye.
Bye-bye.